So far in this course, we've considered simple harmonic motion, the fabulous perfect spring. In this program, we'll be considering vibrating systems with damping and forcing. By the end of the program, you ought to be able to model such systems for yourself, and we'll also show you the differential equations which incorporate these features, and we'll show you some of the properties of the solutions of these differential equations. Now, why should we be interested in these extra complications of damping and forcing? Well, it turns out that in real life, vibrating systems often do exhibit these extra features. For example, the reason that this record was misbehaving was due to the presence of unwanted forcing terms. And by the end of the program, we'll show you how, by the judicious use of damping, we'll actually be able to remedy that behavior. Well, you're probably asking, what has a record deck got to do with a vibrating system? To see that, take a look at this model of a tone arm. Now, it's springy. You see, when I press it down, it vibrates, and the vibrations die away. So actually, it's a vibrating system with damping. So the first thing we ought to do is to look at a vibrating system in the presence of damping forces.
This spring mass system is very much the sort of thing that we were studying last week. That motion is really a pretty good approximation to simple harmonic motion. The decrease of the amplitude with time is barely perceptible. So I'm going to try to make it a bit harder for the system to vibrate by adding a dashpot. That's simply a piston moving inside a cylinder. And you can see it doesn't make very much difference. I still see only a very modest decrease of the amplitude with time. So let's make it a bit more difficult by making that piston move through a liquid, in this case water. And now you can see the effect of damping. There's really quite a marked decrease of the amplitude with time. So let's make it even more difficult by using a liquid that's even more viscous, like oil. And now you see something quite new. With enough damping, the system simply returns to its static position.
So, can we provide a model to predict David's experimental results? Well, the first thing to do is to draw a diagram, and here's mine. It's our old beloved mass spring system, and I've chosen a fixed origin from which to measure the position x of my particle, and then I can apply Newton's second law in the form mass times acceleration equals the forces acting on the particle. Now, what are these forces? There's the force of gravity acting in the sense of x. That gives me this plus mg term. And then there's the force due to the spring. That's just the extension, x minus L0, times the stiffness, k. And in my configuration with the spring extended, that comes in with a minus sign. Now, what about the damping? Well, I've represented that diagrammatically by this. It's a perfect dashpot. And we'll assume that this exerts a force which is proportional to the relative velocity of the piston with respect to the sides of the dashpot. Now, that constant of proportionality I'll call R, the dashpot constant. So that means that I've got another force to consider. It's just R times the velocity x dot. And again, in my configuration, this comes in with a minus sign. So that's my differential equation. It's not too complicated. I can simplify somewhat by bringing these terms to the left-hand side. And now I know from Unit 6 that the solution to this equation, the general solution, consists of a particular solution. And because the right-hand side is constant, in this case, a particular solution can be a constant plus the complementary function. Now, the complementary function is just the general solution to the homogeneous differential equation that's got by putting the right-hand side equal to 0. Now, That I can get by using the auxiliary equation. Remember, that just is the algebraic quadratic equation you get by trying x equals e to the lambda t. Now that quadratic equation will have two roots lambda expressed in terms of the constants m, r, and k. And for simplicity, I've defined a new constant alpha, the damping factor, which is just some simple function of the dashpot constant r. Well, let's have a look at what this quadratic equation gives us. In fact, there are going to be three cases. When alpha is less than 1, then I'm going to get complex roots. That corresponds to a complex exponent, and that gives me oscillatory behavior. When alpha is greater than 1, then I'm going to get real roots, and that gives me an exponential decay. And the critical case when alpha equals 1, well, that gives me equal roots, and that corresponds to critical damping. That gives me the fastest decay to the static solution. Well, these are the theoretical predictions I get from my theory. Now, how do they agree with experiment?
Well, I think you'll agree that there's quite a nice qualitative agreement between Alan's predictions and what I observe with my system. These damped oscillations here are what he described by a damping factor less than unity. And this straight return to the static position is what he described by a damping factor greater than or equal to unity. Now, there are more stringent tests that you can subject his model to, and after the program, it'll be your job to take measurements from this trace and to see just how well his model fares. But that's really all I want to say about simple damping. However, before we begin to look at a real system, like a record player, we need to make a study of forced vibrations. And this apparatus here has been specially designed to show the important characteristics of forced vibrations. It turns out to be described by a differential equation in section 2 of the text. Let me show you the key ingredients of the system. First of all, there's an object here, and that can vibrate at the end of a spring, like that. And there's a dashpot in the system. It's, in fact, all the way back here. And the geometry of this apparatus has been designed to let me vary the damping. It turns out that if I move this dashpot nearer to the spring, then that increases the damping. Okay, now that's our system, but how is it forced to vibrate? Well, there's a cam, an eccentrically mounted wheel driven by a motor. And that makes the bottom of the spring oscillate up and down in a way that we control. You can see on the bottom trace here just how we're forcing the bottom of the spring to move. Sinusoidally, with constant amplitude and constant frequency. And how does the object respond? How is it moving? Well, we've shown that on the top trace. And there are two things I want you to notice. First of all, the output frequency here is the same as the input frequency here. Secondly, the amplitudes are different. The particle is moving with a bigger amplitude than the bottom of the spring. That's just for one particular forcing frequency. What will happen if we increase the input frequency? You can see on the bottom trace that we've got a higher input frequency, but the same input amplitude. And now look at the output of the system. Really much more dramatic. You can see the output amplitude has got even bigger. So if I increase the input frequency even further, will I get an even bigger output? No. At this higher forcing frequency, the output is less dramatic than it was before. Now, what I want to do is to find a way of presenting the observations that I've made on this system. And to do that, I've started to plot a graph. On the vertical axis, I'm plotting the output amplitude, the size of the oscillations of the object, divided by the input amplitude, the size of the oscillations produced by the cam. And I'm showing how that depends upon omega, which is the frequency at which I'm forcing the system with this motor. Now, so far, I've only got 3 results. I found this much amplitude at a low frequency, a lot more at a high frequency, and then it went down again at a even higher frequency. And what we're beginning to see here is a dramatic and a selective response to a certain region of input frequency. That phenomenon is called resonance. And what I'd like right now is a model of this mechanical system and a model that predicts resonance.
First thing is, draw your diagram. Here's mine. This is my spring, and this is my dashpot. And in my configuration, I'll assume that the spring is extended and the particle is moving upward. This is my fixed origin, and the distance of the particle from it is given by x. Newton's law, mass times acceleration equals the forces acting on the particle. This is the force due to gravity minus mg, because it's downwards and against the sense of x. Then there's the force due to the extension of the spring, that's x minus L naught, times the stiffness k, and in my configuration, this comes in with a minus sign, and then there's the dashpot force, the damping force, which is Rx dot, again with a minus sign. Well, so far that's fairly familiar, but what about the forcing term? Well, I'll assume that the bottom has been jogged up and down with a term of distance y for my fixed origin. Now, how does that modify my equation? Well, the only change is, as you can see, in the length of the spring. Instead of x, it's x minus y. So this term becomes this. And that's my equation. It's still a rather simple equation, and if I rearrange it slightly, it's even simpler. And we see on the right-hand side we have this new term y, which gives us a time dependence on the right-hand side. Now, we're interested in the steady-state solution to that equation. You get the steady-state solution by assuming it's of the same form as the right-hand side. Now, the right-hand side, y, we'll assume is sinusoidal. So, it has the form constant plus sinusoid. The steady-state solution, therefore, will have the same form, constant plus sinusoid. Let me use some names here. A0 we'll call the input amplitude. Omega, well, that's the angular frequency of the forcing term. A will be the output amplitude, and phi is just the phase. Now, I can actually, using algebra, find what A is. It's quite tedious, and it's done in the text. If you do that, you'll get this expression. The ratio of the output to the input amplitude is given by this. Well, I can already see some features of that expression just by inspection. For example, when alpha is very small, I can neglect this. Then this term will be very small when omega is equal to omega 0. Now, what is omega 0? Omega 0, in fact, is the natural frequency of the undamped, unforced system. And this alpha is the damping due to the dashpot. So what I've just said is when the damping is negligible, this denominator is small, and the whole expression becomes very big. In other words, for very small damping, I expect to get a resonant behavior, and I've plotted it here, and this is what you get. For alpha 0.1, I get this dramatic selective response, a resonance. Now, when alpha is a bit bigger, 0.3, I still get resonant behavior. It's a bit less dramatic, less selective, but it's still there. For larger values of alpha, the behavior tends to disappear. In fact, you can show after the program that when alpha is greater than 1 over root 2, you're going to get no resonance at all. Well, I've plotted these in a sort of three-dimensional array. Let me tell you what I've plotted here. I've considered values of alpha from very small to larger, and I've plotted the output amplitude against the angular frequency omega, and you can see for small values of alpha, I get this dramatic resonance, and as alpha increases, the resonance becomes less and less dramatic and eventually disappears.
Well, whilst Alan's been formulating his model, I've been accumulating data on how the system actually behaves. What I've been measuring is the ratio of the output amplitude to the input amplitude. That's A over A naught. And I've been measuring that for various values of the forcing frequency, omega. Now, there's something else that I've measured, and that's omega naught. Remember that that's the natural frequency of the system with no damping and no forcing. I've displayed these data graphically, and this is what I'm going to use to test his prediction. But remember that his prediction depends upon the value of the damping factor alpha. For example, for alpha equals 0.1, he's predicting a very dramatic resonance, much more dramatic than I observe. This is his prediction for alpha equals 0.2. And I think that you'll agree that that's in pretty good accord with the data. But remember, that's not all that he predicts. Alan's model tells me what to expect if I increase the damping in my apparatus. The resonance should become less dramatic, less selective, and eventually disappear. So I'm going to test that prediction by increasing the damping. And I do that by moving the dashpot closer to the spring. That gives me a much bigger damping factor. The input that we're going to use this time has a constant amplitude, but gradually increasing frequency. And I want you to look at the top trace to see what the output of the system is. Is there a resonance? Are we seeing a dramatic response in a particular region of frequencies? We're not. All that's happening as we wind up the input frequency is that the output amplitude is getting smaller and smaller. The phenomenon of resonance has completely disappeared. And that gives me even more confidence in Alan's model. And I'd like to remind you just what a simple model it was. A model of a particle moving in one dimension under the influence of a perfect spring and a perfect dashpot. And yet this apparatus, for all its complexity, bears out Alan's predictions remarkably well.
Now, what has all of this got to do with the record that we started the program off with? To see that, let's go back to our big tone arm. Now, we saw that this is a vibrating system which exhibits damping. But I can also incorporate a forcing term which represents the motion of the record up against the stylus, and I can change the frequency of that, and you can see that for certain frequencies it misbehaves quite dramatically. So that's what we want from our model. It's got to predict this behavior, give us resonance, and it's got to tell us the relative motion of the tone arm with respect to the stylus, because that's what gives us the sound that we hear.
And that's your job after the program, to set up and to solve a simple model for the forced vertical vibrations of a tone arm. Now, you won't be able to use Alan's old predictions, because those were for a different system. You'll have to start from scratch. And to help you, I'm going to run through the procedure that you need to follow, stressing the key features involved in modeling forced vibrations. The very first thing you must do is to draw a diagram to represent your conceptual model. And this is mine. A stylus connected by a spring, which I'm modeling as a perfect spring, and a dashpot, perfect dashpot, to a tone arm. And I'm going to model that tone arm as a particle moving in one dimension. The next thing to do is to choose a fixed origin. This is mine, and x is the particle's position relative to that origin. Now you have to consider the forcing point of the system. I'm assuming that the stylus is made to move up and down, and I'm going to label its position by y. Now is the time to look at the forces involved. The force of gravity, the spring force, and the damping force. And to use those forces in Newton's second law. The mass times the acceleration is equal to the total force, which has a contribution from gravity, from the spring, and from the dashpot. Now, that's very much what we've seen before, but you find a new expression for the force due to the dashpot. It involves the relative velocity x dot minus y dot, the velocity which this piston is moving with respect to the pot. Now, most importantly, you must always keep in your mind what it actually is that you're concerned to predict. Alan has asked for a prediction of the motion of the tone arm relative to the stylus. That means x minus y. Let's call that z. What you're going to need is a differential equation for z. And I found what that differential equation is using the equation of motion of the particle. Notice that the time dependence on the right-hand side now comes from y double dot. And you'll find that y double dot is proportional to omega squared, the square of the forcing frequency. And then, finally, what you'll have to do is to find the amplitude of the steady-state solution to your differential equation. Now, I've done that, and the prediction that I find for my model is rather different from Alan's old prediction. There's a factor of omega over omega naught squared in this expression for the response of the system. What that means is that I have to throw away his old predictions for a different system and replace them with my own. This is what he predicted, and this is what I predict for my system. You'll notice the same qualitative behavior. For light damping, there's a resonance, and it gradually disappears as we increase the damping. But there are certain crucial differences. For example, at high frequencies, all these curves go to unity, and that means that the output amplitude is equal to the input amplitude. Now, as a matter of fact, real tone arm systems responding to vertical forcing are reasonably described by a curve rather like this, for a damping factor round about 0.2. There is a resonance, but it's at low frequencies. The manufacturer takes good care that this frequency where the resonance occurs is a lot lower than the frequencies involved in listening to music. So, what's actually happened? What is it that's gone wrong with Alan's record player?
The trouble is, those low frequencies are there, not in the grooves, but actually on the surface of the record itself. You see, this record is really terribly badly warped. Now, all records are warped to some extent, and this can give the sort of trouble that we've been hearing. Is there anything we can do about it? Well, there is. We can increase the damping. And some enterprising firm has actually come up with a miniature dashpot which you can attach to the tone arm, and this actually gives the increased damping that we need. Now, I've attached one of these devices to the identical record deck on the other side of this machine. And when I play the record using that, you'll see there's a great improvement.